Everyone's here now. I'd like to thank everyone for coming to the SEMI-THERM panel discussion, Challenges in Consumer Electronics Cooling. So when I was a little younger, 30 or 40 years ago, to me, consumer electronics meant home audio equipment. That was my life. And I suppose other people were interested in televisions, etc. And the important thing here is that these are boxes, fairly sizable, for the living room. Anything else, any other people who did electronics, it was really just, the realm of hobbyists, ham radio or having a cassette player or something. So fast forward to the present, consumer electronics, and with computation are everywhere. More to the point, they're compact, portable, and stylish. Many are passively cooled, but even the forced convection systems are being elegantly designed, and they're thin and attractive. And now we have devices showing up as wearables, sports monitors, health monitors, VR headsets, a whole new area. Now, as it doesn't take a crystal ball to tell that as computing power continues to become smaller, connectivity expands, and new apps become available, devices are just going to proliferate. And our 5 panelists are working to enable these trends. So each of the panelists will speak to us for 10 minutes, and then we'll have a discussion. We'll be asking for questions from the audience. Have a microphone up here in the front. For right now, we're going to start generally with forced convection devices, then move to passive design, including the all-important ergonomics and temperature control. And then we're going to continue to see if we can, divine some tricks of how to get management and our mechanical friends to include thermal right up front where it needs to be done. With that, I'm going to introduce Andy Delano. Andy, please go ahead and bring your slides up. So Andy leads the Microsoft Surface team's thermal architecture efforts, and he's primarily focused on the Pro product line. Prior to joining Microsoft in 2012, Andy managed R&D with Honeywell and their specialty materials development division and launched some highly successful products. He started his career in '98 as a thermal engineer with HP, working on servers and workstations. While there, he also taught at CU as an adjunct professor, thermo and thermal design systems. And he earned his PhD from Mechie and Georgia Tech, and his thesis was on a single absorption refrigerator walking in the steps of Albert Einstein, one of the things Einstein had worked on. During the first part of his graduate studies, Andy also worked to design the production of the 1996 Olympic torch and spent 6 weeks traveling along with the torch relay. With that, Andy from Microsoft. Thank you.
Thank you, Mark. Okay, so let me orient myself. So I've titled my 10-minute overview, Form Factor Equals Power, but which you may find familiar. One of my colleagues from formerly at Intel mentioned it, but we can go into that later. It's an old term that's probably was originally used on workstations and servers, but I think tablets and consumer electronics and mobile devices, it still applies to them. So let's see if I can show you how. So first I want to go over typical laptop and tablet thermal architectures that we're familiar with, and then talk a little bit about blower limitations in these thin devices. Then we'll talk about tablet cooling, and of course focus quite a bit on Microsoft's Surface Pro, because we've had a lot of fun with this product, enabling it thermally. And then last little quick slide on software thermal control. So if you take the keyboard off of a laptop, you'll see this usually, or something like it. The PCB is here, and the thermal module is there. So that's kind of its control volume. If we zoom in, we see the CPU is under the evaporator portion of the heat pipe. Just to take a step back, sorry, I'll point to this one. There are more people over here. So, and then I need the mic. This is a heat pipe, and this, like I said, is the familiar version of an actively cooled mobile device or laptop. This is where the heat's generated, and we're familiar with heat pipes being considered having an evaporator where the heat goes in, a condenser where the heat's rejected and the fan is located, and an adiabatic section in between. And if you look at infrared images of most of our laptops, they look something like this. You can see, you can see the thermal module. You can usually see where the processor is, and you can see where the airflow is. And okay, so the blowers in these devices, we can often hear them, and they can be not always that pleasant, especially when you realize that very, very thin blowers, and this is Pro 4's blower, you can see how thin it is and how small it is, are particularly inefficient. And I have this slide. I always liked it in engineering class when you'd have a picture with a person in it, so you could get some scale, especially in your thermodynamics book, if they show a steam power plant and you find the person in there. If it's a supercritical power plant, the person was very tiny. So centrifugal blowers can be very efficient, upwards to 90% shaft efficiency, converting the mechanical power into air-moving power. But these are high Reynolds number flows. And when you shrink everything, and I put this character in here to give us an idea of size again, because a person wouldn't really help. These small blowers, in order to be efficient, they would have to spin really, really quickly to get to the same Reynolds number. Plus, they're thin, so there's a lot of leakage. So we found that all of our best efforts, we could only get about 0.6 CFM. And that, at our limitations, and we can talk about this on the panel, that only amounts to about 7 or 8 watts of power. How am I doing? Okay, I better hurry. So with Pro 3, if you take a look at how we can reject heat, we've got power coming in. The device itself has capacitance. We reject heat by the blower, which isn't that much. Natural convection and radiation. And this room is familiar with this, so we can race through it. This is how it kind of stacks out. We could reject about 20 watts with Pro 3. Most of it was by forced convection, but 20 watts isn't that much, given that the processor really wants 15 watts, and it can turbo to 25 watts. So what we started looking at was how can we extend this cooling in other ways, because the blowers were kind of at their limit. So for Pro 4, you see we added a second heat pipe, and we extended the major heat pipe, and we kind of broke the paradigm of heat pipes having evaporator, adiabatic condenser, and kind of used them more as isothermal members or interstates, thermal interstates. And then we had a copper block or copper plate to spread heat further, and you can see that we don't, now our split's different, but our total power is up quite a bit. And Pro 4 is a very powerful device for those of you that have used them. And in fact, they outperform almost all the Ultrabooks for various reasons. For it's called now just Surface Pro, but we always called it Pro 5. We took that even further, and we just got rid of the blower altogether, but you can see we still achieve pretty much the same heat rejection. We grew the thermal module. So you can see we're going from having not too much utilization of the device itself as the heat exchanger to having it where the device itself, all of that surface area is active. And we do have a model of the Pro that still has the blower. Okay, now, is that my overtime?
No, you're fine. You
Okay.
got at least 5 minutes.
Okay.
5 to 7.
I saw the 3-minute. We can go back then with all this time. Okay, so just to put a few more details here. To lead into the next slide, the constraint here, and most of us are familiar with this by now, because when I worked on the design of larger systems, you were worried about junction temperatures always, but then when you get to tablets, it's touch temperatures, because the user ends up feeling the heat before the electronic components get uncomfortable. So these devices are limited to about 48°C touch temperature, and we have to control to that. Now, how we control to that's really quite important. If you've ever had a laptop where you hear the fan cycling on and off, and maybe you notice kind of choppy performance, things get good and then they get slow. This is maybe what's happening. This is a little bit of an eye chart, but this is temperature and power on the y-axis and time. And you can see it. This particular Ultrabook has had a large compute load thrown at it. It turbos at 25 watts for, like 15 or 30 seconds. And then its touch temperature, shown by the blue line there, gets up to the limit. And you can see they're doing a nice job controlling to it. But you can see this kind of wavy behavior in the blue line and also in the processor power. It's fluctuating, plus or minus 1.5 to 2 watts around its mean power. And that results in kind of a poor user experience, and the fan is oscillating. It's really not that pleasant. We take a lot of time with Pro, and here's Pro. When we give it the same power load, Pro can turbo at 25 watts. That's this blue curve right here for almost 200 seconds. That's 155% improvement in compute performance. Then it smoothly settles down to its entitled performance of close to 15 watts. And everything is very stable and steady, and the fan comes up smoothly. And so software, one of our other panel members will be talking about this. Software control is important for these devices, and that's all I have. We've been doing tablets a long time, just to remember that.
Thank you. Next, we're going to hear from Guy Wagner, who is a director at Electronic Cooling Systems. He's in their Rocky Mountain office out in Colorado. 45 years of experience in the electronics industry, which includes IC system cooling and packaging technology, disk drive design, computer system design, and telephone and switching systems. He's considered expert in the cooling of electronic systems and IC packages. He's authored and presented at least 40 papers at international technical conferences, and he's got 29 patents. Prior to joining ECS, Guy was chief scientist at HP in Fort Collins and a member of the technical staff at Bell Labs. Mr. Wagner received his MS in mechanical engineering from Iowa State University.
Okay, where is the icon? Yeah, I'm looking for the full, normally it's down here. There it is. Okay, got it.
This is a running time.
Okay, great. Okay, so if you take a look at the future of computing, it's moving off the desktop and it's moving onto the handhelds and portables, and it's moving into the large data centers in the cloud. So we're going to be looking at the laptops and handhelds and phones and the tablets. Now, when you get to the handheld devices, users are expecting the same type of performance that they used to get on the desktop. So that can't be compromised, and on top of that, they generally consider passive cooling or noiseless active cooling to be the requirement because they don't want to hear fans running. The limiting factor, as Andy said, is not the internal temperatures of the ICs anymore, but the comfortable touch surface temperatures. So if we take a look at touch temperatures, what you see is, let's see if we can make this work. This is increasing conductivity of the case. This is increasing time that the unit or the object is being held. And so when you go from plastic and rubber all the way up to a metal object, the maximum touch temperature drops. when you go from time that it is just touched momentarily until it's held continuously, the maximum touch temperature drops. So I wanted to take a look at the amount of power that could be dissipated, say, from a 10-inch tablet. So I have a 10-inch tablet here. I made the tablet isothermal, in other words, all one temperature, so that by doing that, we get the maximum amount of heat transfer because all surfaces are participating equally in the heat transfer. And when we do that, we get a curve something like this. This is an isothermal tablet. In other words, this is the very best you can do under natural convection from that tablet size and from perfect, push the wrong button. Perfect surface emissivity of 1.0. So when we get down to, if we take a look at the 10-inch tablet, and we consider, say, a 16 Celsius temperature rise of the surface, we can go to around 17 watts. A 9-inch tablet's a little lower, and when we go to a 7-inch tablet, it's around 11 to 12 watts. That's for that temperature rise. If we take a look at the temperature rise on this axis, on the y-axis, or excuse me, the power dissipation on the y-axis, and we take a look at the surface area of the tablet on the x-axis, this is where it falls. Full-size tablet, mini tablet, and smartphone. You can see the smartphone is way down around a maximum of about 3.5 watts for a 16C touch temperature rise. And if we take a look, this is the unit in the vertical position. This is when we put it in the horizontal position and then set it onto a surface like a table, or even if you're using it in bed and you set it on the covers, that bottom surface essentially becomes adiabatic and you do not transfer any heat off of that surface. So you're depending upon all the other exposed surfaces to get rid of the heat. Okay, the problem is that consumers are not willing to give up performance. You're limited to around 17 watts from a 10-inch tablet. And if you want to let the temperature rise go to 20C instead of 16C, you're limited to around 22 watts of power dissipation. Assuming that you already have highly emissive surfaces on it, you're not going to be able to get any more heat transfer due to radiation. Now, one thing I will point out is that a lot of engineers, when they're doing natural convection problems, they neglect radiation. This is a really serious problem because if we take a look at the percentage of heat that actually leaves the tablet, it's more than under convection. It's around 55% with a highly emissive surface. Okay, now, the only thing you can do after you've reached the limits of natural convection is to put a small air mover inside. And I ran several curves. This starts at 0 CFM, which would be natural convection. Here's your temperature rise, 16C or 20C allowable. And then this is with 0.2 CFM air flowing through 0.4, 0.6, 0.8. You'll notice that we get increasing power dissipation, or we can say that as the amount of airflow through the tablet increases, we can dissipate more and more power. The real problem is that at some point, we get objectionable acoustic noise. So, as Andy said, we're pretty well limited to around 0.6 CFM for, say, something the size of the Surface Pro. If you take a look at this, this is the tablet airflow across the x-axis, and you have the amount of heat that is actually removed by the blower as the airflow increases, and you have the amount of heat that is removed by natural convection on the outside and the amount of heat removed by radiation. Both of those drop as the amount of heat increases that is moved by the blower, because the outside of the tablet is becoming cooler, so it decreases these two quantities and this one increases. But you'll notice that at about 0.6 CFM, both the natural convection and the radiation component are still greater than the amount of heat removed by the blower. So that pretty well concludes what I want to say for right now, and we can save questions for later. Thank you.
And every time I've had to do a tablet design, the first thing I do is that calculation to see what the maximum power is, because that way I can go back to management and say, this is it. As long as we're on this planet, nothing will get any better. Emil, please come join us. Emil Rahim is a senior thermal engineer at Google, where he leads the architecture of multiple consumer devices. Prior to joining Google, Emil worked as a thermal engineer with focus on consumer electronics, again, at Electronics Cooling Solutions, but also at Qualcomm, Amazon's Lab 126, and GoPro. Emil holds a doctorate in mechanical engineering from the University of Maryland, and he has authored and co-authored 5 journal articles, 13 conference publications, and 4 published patents. Thank you.
Thank you. Thanks. So this is basically the one slide that has all the content that I'm going to talk about today. As both Andy and Guy mentioned, form factor is very important. It's critical for our design. It more or less dictates the maximum power, especially in passive cooling when we don't want to have any kind of forced convection. All consumer devices, no exception, are getting smaller, thinner, and we're dealing with the problem that we're reaching our skin limit way before the junction temperature of 90 or 95 degrees C is reached. So as you can see here on top, I just put some examples. So you can see on the top left, you can see this is Google's AI-powered camera. It can be body-mounted, or it can be mounted on your bike or on basically anything in the house. You have smart earbuds right now that do the translation or interpretation. There's some computational power that's contained in an extremely small form factor that's body-mounted and wearable, basically. And of course, we all know, we're all familiar with the VR and the VR headsets and how much power, especially standalone systems, not only the ones that hold your phone, and where a lot of processing power is actually mounted on the body. Other examples, action cameras are expected, and they always do, especially with 4K and 4K 60 capturing. Home devices like smart speakers, like Google Home Mini, shown here, as well as the Wi-Fi router. So in all these, there's not a single standard we can follow. There's not a single spec. And this is one of the biggest challenges when working on these devices. So the second point here is the ergonomic limit. So as I mentioned, we don't have a single spec to follow. There are some safety limits and some compliance limits, but these are way too high. These are of the order of, they allow plastic temperatures to run as high as close to 90 degrees C and 40 degrees C ambient. And this is extremely uncomfortable. As you can see also, there were medical research that I found recently was done in the UK, and this is the chart on the bottom right. These are different material, so the one on top basically have lower conductivity, and the conductivity increase as we move down. The one on the bottom is the locus or the curve for copper. As also Andy and Guy mentioned, that we can tolerate higher temperature if we're touching it only for a quarter of a second, as you can see the first data point, 0.25. However, the important thing with this study is they tested on volunteers, and I'm glad I wasn't one of those volunteers, that regardless of the material you're holding, if you touch it long enough, even at what we would think are relatively low temperature of limit of 43 degrees C here, it's enough to cause burn on the human skin. So this is kind of a new problem for us, especially that we're working on. We already, like Google already released a wearable camera, and there are other wearable devices that many other consumer devices producers have in the pipeline. And we do need better understanding. We do need more user studies and hopefully some sort of a collaboration that would help us define certain spec for safety that's better than what's available right now. One other important thing, and I experienced this having worked at companies that value customers' feedback and surveys, is the perception of the customer is extremely unpredictable, I would say. Sometimes when the device is perceived as doing a lot of computing, anything basically with a display, we notice that the customer is much more forgiving than when a device such as a router or a smart home speaker is perceived. So what's perceived as hot for a home speaker, we would test and we would see that this is well within any spec, within any norm. It's mildly warm. Just because the device is perceived as idle, the customer would have a complaint about it. So this, again, brings us to the lack of any spec or any standard in that regard. So this is basically the summary, and this is one of the biggest challenges I've seen working on consumer devices, and I will conclude with that and be happy to take questions at the end. Thank you.
Okay, so far all of us who've spoken come to consumer electronics cooling from the heat transfer perspective. Gabriel Khouri has been in consumer electronics for a long time from the mechanical design and management perspective. He's currently the Director of Engineering and Drone Development at Intel, and he's led thermal and mechanical engineering for over 25 years. Now, in the past 5, he's led teams in product design, exploration, feasibility, and innovation in various electronics industries, such as mobility, converged computing, ambient computing, virtual reality, and drone technology. At least one of the devices you've seen that our CEO waved at CES during his keynote and said, this is the thinnest tablet, or this is the first, et cetera. That was a project that Gabriel managed. Prior to Intel, Gabriel led product development at Motorola. So all those years you walked around with various Motorola flip phones, those came out of his departments too. He's also, and he just played a role bringing a multitude of products to the global market from Motorola. He has an MBA, but his engineering degree is from Georgia Tech. Thank you.
Thank you, Mark. So Mark had asked me to kind of put a little practicality around the thermal design. We heard a lot of theory from experts, and most important is when it comes into market to productize it. It's not obvious. Thermal designers only cannot make it happen. So there has to be a collaboration overall. So I will talk a little bit about the cross-functional collaboration, more specifically about the dynamics of mechanical design versus thermal design in execution. I will also take a general look at the passive thermal mechanical system and and how we can always achieve what we all talked about, which is always satisfying the expectation. There is such a multitude of devices that the expectations are like unwritten already. The consumer wants the sleekest, the smallest, the most powerful, et cetera, et cetera. All this, when you translate it into engineering terms, that means packing very high power in a small enclosure. So how do we do to get this thermal design that we showed all the theories about into small packages? I guess in different areas, it's you have to start very early first in the foundation of things, because otherwise you'll be playing catch up or you'll never converge to the end. You have to, for example, influence even the electrical designers on where to place your highest point load, how to do the distribution of it, which structure of PCB it is so you can pipe the heat properly. Try to combine the functionality, the different functionalities in one single part so you can collapse everything all together, all the layers together. Integrate certain layers within each other, even though they're like different functions. And I'll show some example. And most important part that I think Andy talked most about is how do you take the highest power or temperature point and pipe it out and then cool it. This is like crucial. When it comes to productization and manufacturing, if you don't have a robust mechanical system that can be repeatable across unit to unit, then the product has no value. So looking at the cross functions, there is always a conflict when a product scope come together. And the very successful products have very strong conflicts. And the good conflicts is what brings the good stuff out. So if you look at the interaction between software and thermal management, or workload, how the software interacts and how much, Andy mentioned turbo and different times of certain power at peak and et cetera, et cetera. And it's how smart we go about it. This has to all start in the beginning. Even in the industrial design, when you say we talked about skin temperatures, well, we have to hedge our bets. How do we select the pretty materials at the same time as the efficient ones to spread the heat, to pipe all of this together, to keep everything, all the package in the right size. Same as a supply chain. Sometimes you use ingenuity to use existing things to make them happen. Sometimes you go to suppliers who are doing new things to bring them in. But if you don't start early, they never materialize. I guess we can write books about this, right? So I'll just go on. I think I gave a few examples that that illustrate that. So overall, every time we bring something we productize something, we bring a product to the market, there are like 4 main phases: conceptual, then design, then verification, then we produce. And there are like a little bit more granularization here, where I show that if this feasibility time wasn't used for thermal design and simulation and bringing up what exactly our intuition, what we want, the product we want to make, and identifying a thermal solution. If we don't identify that thermal solution early on into the hardware execution design, it will never go in there. If we try to do it after the fact, it's not going to happen. I remember when I was a design engineer, we never thought about thermal stuff because it wasn't a problem. I started with very simple devices. They were pagers, and then more two-way devices, and then mobile phones, and etc. So at some point within like maybe 2-3 years of my start, we started seeing that the products were choking, and we found out because of thermal problems. And it was easy to just patch them and make it work. But later on, you had to take these things seriously. You had to think fundamentally from the beginning. Otherwise, you would never make it. So in this, if the thermal solution is not kind of simulated and well thought through up front in here, it's not going to go in. And if we attempt to go without it, and then we wait all the way until a product comes together over here, that means we have to go and start all over in the beginning, from the beginning. And that could be 3 to 5 months work. So a project becomes, instead of being like 9 months to a year, it can become a 2-year ordeal. So, and usually the way I do things, I always try to get everything worked up in the front, predict where you don't know, and that's the choice that this is the only choice you have. And then right before making the physical, try to make a one-of to prove the theory that was started in the beginning. And then once I see that it tallies, then I know that there's going to be minimum waste of time. And optimization is what it's what it is. So in general, when we look at, this is an example of a handheld device. It could be a tablet or a phone. And you look from the top up, from the display all the way down to rear housing. Depending on, I said that we have to combine things together. We have to work with different disciplines to make it happen. In the mechanical design, you choose to usually design either a monocoque and top it up with something so you have a strong 3D construction, or some other manufacturers try to do a chassis and they wrap it. They always have a strong member that monitors everything. So sometimes that display can be on its own strong enough to top with the rest of the housing. Sometimes you have to make a separate layer. In this example, I will show later on where this layer could be a spreader, an EMI layer where it stops all interferences with all the RF devices. It could be also a support for the glass from breaking during dynamic shock. And in certain instances, I saw it as being regulatory fire enclosure because it would be good for the FCC passing or different regulatory requirement. As we go into it, this is usually the SoC is the highest, most concentrated power, and we choose on how we're going to do the interface. This is also a very mechanical system, very hardware in means of electrical engineering. When all the engineers get together to do this early on, this is when it is successful. It's done in minimum time. Most of the work is done up front and not later. In this example, this is a small tablet that has a computer-like power. It's a low-power PC that we put into a 5.6-inch device. And to keep the small form factor, to keep it product-like, we had to do a lot of gymnastics around every layer of the system. And this is the typical support layer that I was talking about, which did all 4 functions. In getting the heat out, the hardest part is how you put this copper plate. This device was about 7 millimeter. Putting a copper plate there, bolting it down, takes a lot of space. Putting holes through the PC board eats up PC board space and makes it wider, so on and so forth. So we had to design like a clip system around the shield where we combine the shield to be that plate that Andy talked about. In the rear housing, we had to go to a vapor chamber because the powers were very high. A vapor chamber usually is very thick, so we had to work with suppliers to bring it down to 0.55. We had to embed it in its chassis in the rear housing to keep it from affecting the entire thickness. And this is how it came together as a product like, and it was demonstrated. We built about 500 of them. So without working very closely with all the different factions of the multidiscipline, it would have been impossible to do that. That's it for me.
Okay, thank you. May I have a round for all of our panelists, please?